Welcome to Lesson 3B, Numerical Solutions of First-Order ODEs. In this lesson, we'll discuss numerical solutions of first-order ordinary differential equations. Specifically, I'll explain the Runge-Kutta technique, and I'll do some example problems with it. By way of review, in the previous lesson we talked about analytical solutions of first-order ODEs. When you have constant coefficients a and b, we can solve this standard form of the ODE for y as a function of time. Here's an alternate expression. And we also defined the half-life and the first-order time constant and the steady-state value. But what if a and b are not constants? Well, in that case, we'll have to do a numerical solution. As I say here, there are many numerical techniques applicable. The only one I'll be talking about is the Runge-Kutta technique. It's one of the simplest ones to understand and to code. I'll give a quick overview of the Runge-Kutta technique. You can go to my website and look at this learning module for more details, or follow my notes here. Here's the standard form of our equation. We start at t equals 0 with some known y, and then we want to march in time, calculating y along the way. I'll explain how the Runge-Kutta technique is used to march along in time. You can read some of this other stuff later on your own. As a simple-minded algorithm, we use the explicit Euler method, where at the new time step, y is equal to the old time step, plus the increment of time times the slope evaluated at the old time step. From our equation, this is the slope. I illustrate this graphically, where at time tn, we want to march to tn plus 1, so we calculate the slope here and extrapolate to this point. The problem is it's very far from the exact curve. If you make your time step very small, you'll get closer, but the error will keep increasing as you go along. It also can be unstable, so this is not a very good method. People have developed other clever algorithms that are of higher order accuracy, such as predictor-corrector techniques. The Runge-Kutta technique we'll talk about is fourth order accurate. The final value at the next time step is the value at the old time step plus some increment, where that increment is a weighted average of 4 trial increments. Again, this is best illustrated graphically. The first guess uses the slope at time tn just like the Euler method, but instead of going all the way to tn plus 1, we go to tn plus a half, halfway. Then we calculate the slope there, again based on our equation for the ODE. Using that slope, we come to this point, and we calculate the slope there, and then using that slope, we calculate this point all the way. So we're kind of predicting and correcting several times here. The final value is a weighted average of these 4 increments. Here's the equation for the final increment. It's a weighted average because these 2 are weighted more heavily than the outer 2. Here are the details. To calculate delta y1, we use the explicit Euler method, and then we take a slope halfway, as I described on the plot. We keep doing that for all the intermediate steps, until finally we use equations 4 and 5, which I showed previously, and this final result for the delta y final, which we then plug into here to get the next step. As I already mentioned, the 2 inner slopes are considered twice as important as the 2 outer slopes. The final predicted point is still not going to be exactly the same as the exact curve, but it will be very close. And as you make your delta t smaller, the error will get extremely small to fourth order accuracy. Finally, I comment here that this technique can be applied to more than one differential equation at a time. You can even solve nth order ODEs by splitting them into n first order ODEs and then solving those simultaneously. I'll illustrate this with an example. This is the same example as the previous lesson. Here's our first order ODE in standard form and our initial value. So b is 10.0 and a is 3.82 based on the standard form of our ODE. I solved this using the Runge-Kutta technique in both MATLAB and Excel. Here's the MATLAB code. Again, you can download this and copy it and paste it if you want. This subroutine is built into MATLAB, where you need the derivatives, the span of the time, and this is the independent and this is the dependent variable. There's some plotting stuff, some printing stuff, and that's about it. The important thing here is this function for the derivatives. I set a and b, and then dy dt, the slope, comes from our standard equation for the first order ODE. When you run this, here's the result. You see that we start at 7.6, and by the time we reach about 2, this thing has flattened out, and you can see the first order behavior. I also did it in Excel, and here's my result. You can see that we get the same answers. I posted both the MATLAB and Excel files that I used to solve and construct these plots Where can we download those files, Professor? If you click on the details about this YouTube video, you'll see a link where you can download these files. Okay, thanks. Finally, I'll do a live demo using Excel when we have non-constant coefficients. Here's my Excel file where I did the case with constant coefficients. I pick a start time, which is 0, a time increment, which you can adjust as needed, and then the starting value. And these two columns represent the variables t and y as we march along. Here's our coefficients a and b. You can see that a and b are constant here. All of these are the intermediate steps using the equations that I showed you. And then the final equation is this weighted average of all the incremental values. As I march along, I set this next y to the previous one here, and I just filled everything down. My second sheet here has a plot of y versus t. Now what happens if one of these coefficients is not constant? Suppose that b is a function of time. I'll make it a sinusoidal function, so b is equal to 10 minus 12 times the sine of 20 times t, which is cell A13, close parentheses. If I double click, you can see the equation here. When t equals 0, this is equal to 10. But now I fill this down. You can either do this and go all the way to the bottom, or if I undo that, just double click on this little box and it fills it down the entire way. Now my plot looks like this. We still have the overall behavior of the first order system, but I've added some oscillations to the result. A can also be a function of time. You would change that here in this cell and then fill down. The bottom line is that this is very useful. We will apply this Runge-Kutta technique to solve many problems in this course. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3. That's all there is to it.